In the next, we now have the derivative, the gradient of the loss function with respect to the output of the network. And in the next step, we will backpropagate this gradient through all layers of computation of the network, and therefore we will be able to calculate to which direction we should adjust the model parameters, therefore to change the loss function to the desired direction, that is to reduce the loss function. So the computation, the computation is implemented through a method. Let us call that backward propagation. Have the self, and we will have the gradient of the output. We call that d loss with y. So let's call that dy. And in this particular denotation, let us call that dp. So in the first step, we will calculate how the b will affect the output. Now notice that in this how b will affect that output. Notice that in this denotation, we call this p. And the p is calculated through b using this sigmoid function, 1 plus epsilon to the power of minus b. So we want to calculate this, how b affects the output of this. The calculation is a bit technical, but the final result is very simple. So to take this, we will have, consider this is a polynomial with, this is to a general sense it's polynomial, but the power is minus 1, so 1 plus. That is minus 1 times to the power of minus 2, and this is multiplied by the derivative of we can remove this because this will not affect the derivative of we have every elements here ready. We write out all the elements now as that is epsilon to the power of minus b. Again, the same. And for this one, this minus 1. And this will cancel with this. So write it out. We have so this is the network output P itself, and this is 1 minus P. If you write 1 as, and the P is of course using the same denominator, and the numerator is 1. So remove these two, you get this item. The calculation is element-wise. Therefore, we can calculate that element-wise as well. So the calculation goes this way. We will calculate dB, and immediately we will find that it's better to have this result cached during the process of the computation. So we can use this. Therefore, we can use this as something like y minus self.p times self.p. So to cache the value, we save it as a property, as an attribute of the object, and seemingly we will cache all the other intermediate results. So we have finished the first step of backpropagation. And in the next step, we have the B is the result of H with matrix multiplication of and U. So now we have dB. We will backpropagate this gradient to dH and du. For dH, for the parameter du, we can use the similar calculation of this where we have discussed in the lecture. We discussed backpropagation in matrix format. We use this. We collect the contribution of the parameter matrix to the result of the matrix multiplication and get the result of the derivative of the matrix parameter matrix as this one. So, but we substitute x using h, the input, and substitute the parameter matrix, the w using u, and the output of a, and in this case would be b. So our code would be the u is numpy dot matrix multiplication, and we will have soft dot b dot transpose times the dB, the just calculated derivative, the calculate b gradient. And for this part, the h, we need also to backpropagate the gradient from this. Now we have the gradient of this, but we will also need to calculate the gradient of dh. Therefore, we can further backpropagate to this parameter matrix and so on and so forth. To calculate this, let's consider, and it's the way of calculating considering the contribution of elements to the output of the matrix multiplication is very similar. I think a technique is to concentrate on the shape in the matrix computation, and therefore, if you make the shape right, probably you get the computations correct. So the B, let's consider, is now n samples by q attributes, output attributes matrix, and now we have calculated the gradient of the loss function with respect to B. We know how each of the elements in B affect the final output, final loss function, and then we want to consider now we have the u, and the u at this stage is keep fixed, and u of course has q columns. Therefore, you can have h times u to give it to B, and u have p rows. Therefore, it will be take the inner product of the p rows in H, and H has n rows, and U here is considered as constant because we have already done in the previous step here to calculate the derivative for U already, and now we are considering how to calculate the derivative of H, the dH. Let's write it down, dH. Let us consider a particular element H, such as the one in the left top corner. How this element contribute to the matrix multiplication B. It will participate in the computation of taking this inner product to arrive at the first element in the first row and first column. It will also again participate the computation of the second element in B, but this time we'll be combining with the element in the second column in U, so on and so forth. Therefore, to propagate the contribution, how B contributes the change of the loss function, we will combine the B's contribution to the loss function with the elements in U and give that to how the first element, how this element in H will contribute to the change of the element, will contribute to the change of the loss function. So therefore, to do this, we will have another matrix multiplication, and the length Q dimension will serve as the inner product dimension of the matrix multiplication. So therefore, we will have, of course, the n dimension will be the first dimension of the outer, because outer product, because dh will have n rows. So we will write it as a db and times, because db will have q inner here, and there will have u transpose. And therefore, we can write it in this way. Let me move this a little bit here, and the numpy db. Oh, I think I have made I have done a typo here. Here should be dp. Oh, db. But then here should be h.t. Okay, and here I will have db times u dot transpose. And similarly, I will have the, okay, I think I need to multiply the, using the chain rule to multiply the derivative, the gradient of the P, how the output, that is how B affected the output of the network, and this will be how the output of the network affects the loss function. So we need to add this part here. So correspondingly, we will have dA equals 1 minus self dot A times self dot A times dH, and also correspondingly we have dW is numpy dot self dot x. Therefore, we need to cache the x here. That in this way, we save the data we received from the last step of forward computation and use that in the computation of the derivative of the parameter matrix. Okay, I think in this way we have done the calculation of the backpropagation algorithm. We stop here for this part. In the next video, let us test numerically as what we have done before of the calculated derivatives of the parameters.